Aqueous solutions. Many qualitative and quantitative chemical reactions are in aqueous solutions, and we use water because it's convenient and cheap. Electrolytes, non-electrolytes, and weak electrolytes. Ionic solutions can be identified by their ability to conduct electricity. If a large number of ions are present in a solution, the solution will be an excellent conductor for electricity. Such a substance is completely ionized and is a strong electrolyte. Something that is completely ionized is a strong electrolyte. All soluble ionic compounds, all strong and weak acids, and very, very few molecular compounds are electrolytes. Notice how it says all soluble ionic compounds, meaning the ones that have, right, Na, K, NH4, and NO3. If the solution conducts electricity only weakly, there is likely to be only a few ions. So if a weak electricity, the substance is partially ionized and is a weak electrolyte, such as weak acids and weak bases. So all those weak acids and weak bases, they do conduct electricity. They're just weak because they only partially create ions. Partially they're a precipitate, partially they create ions. Non-electrolytes have no ions and therefore do not conduct electricity. Such as pure water cannot conduct electricity. Solubility in ionic equations. In order to understand what is happening as substances interact with water, we can use ionic equations to show the ionization. So a strong electrolyte breaks apart entirely into its ions. A weak electrolyte only partially breaks into its ions. So we see an arrow going in two ways. Later on in the year, we'll use those pretty often. And a non-electrolyte has no ionization. It doesn't break apart into ions. There's a summary of all of this here, and a couple questions 1 through 5 on the next page. Now we'll continue with expressing concentration of an electrolyte. In other words, molarity. So for molarity, we can use the relative concentrations of the ions in relation to the compound based off of the formula. So just like when we talked about how many moles of oxygen are in CO2, there are 2 moles of oxygen in every 1 mole of CO2. Well then for a 1 molar NaCl, there's 1 molar Na ions and 1 molar Cl ions. For 1 molar Na2SO4, there's 2 molar Na ions and 1 molar SO4, 2 minus ions. Fix this typo here. It's not 42 minus ions, it's SO4. Pop the 2 minus to the top. So the definition of molarity contains 3 quantities. We have molarity, moles of solute, and liters of solution. If we know any 2 of these, we can always calculate the third. So anytime we're dealing with molarity, try and find moles or try and find liters. You must have the other one already. Dimensional analysis is going to be used with this. For molarity, we have molarity equals moles over liter. This infographic on the side is how you would make a solution with an exact molarity. You'd calculate how many grams you need for the exact moles you need, and then fill with water to the correct liters. You'd have moles per liter. So for number 1, calcium hydroxide reacts with hydrochloric acid to produce calcium chloride and dihydrogen monoxide. Calcium hydroxide, CaOH2. It's a base, so we know it is aqueous. Reacts with hydrochloric acid. It's an acid, so we know that it's aqueous. To form calcium chloride. CaCl2. Now to find this state of matter, we need to think about our solubility rule. It does not have Na, K, NO3, or NH4. So we will assume solid. Plus dihydrogen monoxide, H2O. And unless otherwise stated, you always put H2O as a liquid. I don't have aqueous on both sides, so I wouldn't be able to do a net ionic in this case had it asked for one. Now to balance this, I need a 2 and a 2. So for part B, how many liters of 0.1 molar HCl would be required to react completely with 5 grams of calcium hydroxide? So we'll start with our given. Now this wants liters, but I can't use that 22.4 because it's not a gas and it doesn't say it's an STP. So the only way I'm going to get to liters is by using this molarity. I have molarity, so I have this, I want this, so I need to find moles. I can easily do that. I can go from 5 grams of calcium hydroxide to moles of HCl with one line of stoichiometry, right? So I have 5.00 grams calcium hydroxide grams calcium hydroxide, OH2, to moles, and then moles of calcium hydroxide to moles of HCl. Using my balanced equation, I have 2 moles of HCl per 1 mole of calcium hydroxide. It will be grams per 1 mole. I find my molar mass on my periodic table, 74.09. Multiply the top, divide by the bottom, and I get 0.135 moles HCl. Now I'm wanting to find liters. Put that over liters and it will equal my molarity, which was 0.100 molar. Solve for liters. I get 1.35 liters of HCl. That is how much HCl I would need to react completely with the 5 grams of calcium hydroxide. For the next one, if I combine 15 grams of calcium hydroxide with 75 milliliters of 0.5 molar HCl, how many grams of calcium chloride would be formed? I have 2 starting amounts for 2 reactants, asking for the amount of product produced. That's a limiting reactant problem. Now the only difference between this and what we've always done is instead of starting with grams or atoms or liters or moles, we started with molarity with milliliters. We can easily find moles from there. So if I use what I've given 0.500 molar HCl, that equals X, I want my moles, over 0.075 liters. Okay, molarity, moliters, moles over liters. Once you solve for your moles, you have 2 starting amounts, and you proceed as normal to find the amount of product based off your limiting reactant. Identify your limiting reactant for part D, and then find out how much excess, just like you always have. There's no difference between this and what we've already done except for just applying molarity into it. Your homework will be to complete through page 6. There's 3 more problems on the next page.